Enough sunlight strikes our planet in 1 hour to power human civilization for an entire year. We are surrounded by this staggering abundance, yet we remain locked in a cycle of scarcity, dependent on ancient fuels buried deep beneath our feet. This video explores the radical solution emerging from the final frontier, building mega arrays of solar satellites to power the entire planet. By the end, you will understand how this single endeavor could permanently rewrite the rules of global energy, geopolitics, and human potential. We will uncover why this idea was abandoned for decades and what secret breakthroughs are now bringing it back from the brink of science fiction. How will we react when the ultimate source of power is no longer beneath our feet, but silently watching from the sky above? The dream of capturing sunlight from space did not begin in a laboratory or a government report. It began with a story. In 1941, a young writer named Isaac Asimov published a short story titled Reason. In it, he described a space station that collected solar energy and transmitted it to planets as a focused beam of microwaves. At the time, this was pure speculative fiction, a clever plot device in a tale about robots and logic. Yet within that fictional framework lay a seed of profound insight, a vision of energy without wires, without borders, drawn directly from the source. For decades, this idea remained confined to the pages of science fiction, a tantalizing what if that seemed forever out of reach. That changed in 1968 when a scientist named Dr. Peter Glaser looked at Asimov's fictional concept and asked a simple, revolutionary question. What if we could actually build it? Dr. Glaser secured a patent for a practical solar power satellite system, transforming the idea from a storybook notion into a formal engineering blueprint. His design was audacious, a colossal structure in geostationary orbit, converting sunlight to electricity and beaming it down to a receiving antenna on Earth. This was the spark that ignited serious scientific interest. Throughout the 1970s, agencies like NASA and the United States Department of Energy conducted extensive studies. Their conclusion was both encouraging and frustrating. The concept was technically feasible, the physics checked out, there was no fundamental law of nature standing in the way. But the economics were a different story. The estimated price tag was astronomical, requiring launch costs thousands of times cheaper than what was possible with the technology of the era, like the newly developed space shuttle. The vision was clear, but the path to get there was impossibly expensive. So the reports were filed away and the dream of space-based solar power was shelved, labeled a technology for the distant future. It was not declared impossible, merely impractical. This historical pause is crucial to understand because it frames the entire modern revival not as a new idea, but as an old one whose time has finally come. The dream was never abandoned, it was simply waiting, silently orbiting in the realm of possibility, for the world to change enough to make it real. The fundamental advantage lies not in a new kind of solar panel, but in a new place to put it. Here on Earth, our solar farms wage a constant, losing battle against the sky. Sunlight must first pass through a turbulent ocean of air, scattering its energy. Clouds drift by, casting long, unproductive shadows. And of course, the planet itself turns, plunging every panel into darkness for nearly half of every day. These are the unavoidable limitations of a terrestrial energy source. But step outside our atmospheric bubble into the silent vacuum of space, and every one of those limitations vanishes. There is no air, so sunlight arrives undiluted and far more intense. There are no clouds, only the perpetual, unfiltered glare of the sun, and in a carefully chosen orbit there is no night. A satellite can be positioned to bask in continuous sunlight 24 hours a day, 365 days a year, This is the simple, profound why. Space offers what Earth simply cannot: perfect, uninterrupted access to the source. So how would such a system actually work? The core architecture is elegant in its logic. First, imagine a constellation of vast, lightweight solar arrays, not in low orbit, but much farther out in what is called geostationary orbit. This is a special belt about 22,000 miles above the equator, where a satellite's speed matches the Earth's rotation. From the ground, it appears to hang motionless in the sky, a fixed point of reference. This is crucial because it means the receiving station on Earth can have a permanent, unwavering link to its power source overhead. These sprawling arrays, likely kilometers across, would do one job exceptionally well: convert that relentless stream of sunlight into electricity with incredible efficiency. But electricity in orbit is useless to us down here. This is where the system performs its true magic trick: wireless power transmission. The generated electricity is fed into a transmitter, which converts it into either a focused beam of low-intensity microwaves or a precisely aimed laser beam. This beam, carefully calibrated for safety, is then directed down toward Earth. It travels the tens of thousands of miles back through the atmosphere, where it is caught by a massive receiving station on the ground called a Rectenna. This is not a giant battery, but a sprawling grid of specialized antennas designed to absorb the incoming beam and convert it back into clean, usable electricity for the grid. The efficiency of this two-way conversion, from sunlight to electricity to beam and back again, is the single greatest engineering challenge. It is the linchpin that determines whether the whole audacious concept is a viable power plant or a fascinating but wasteful experiment. For now, hold that thought, because the journey of that beam from orbit to your home outlet is a story of physics, precision, and a quiet revolution in technology. That beam of energy faces its first and most formidable obstacle before it even leaves the ground. We must first build the source, and the scale of that construction defies every earthly reference point we have. The term mega-array begins to feel like an understatement. To generate power equivalent to a single large nuclear or coal plant here on Earth, a solar power satellite would likely need a solar collector spanning several square kilometers, a floating island of technology larger than many city centers. Now expand that vision to meet a substantial portion of, or even the entire planet's, electricity demand. We are no longer discussing a single structure, but vast constellations in the sky, with a combined surface area reaching into the hundreds or thousands of square kilometers. This is not merely building a new kind of power station. It is the single largest construction project in human history, and it must be assembled in the most hostile environment imaginable: high Earth orbit. The numbers become almost abstract in their enormity. The mass of materials required would be millions of tons. Using today's most powerful rockets, it would require not dozens, not hundreds, but potentially tens of thousands of dedicated launches to ferry all that material to space. To visualize this, consider the International Space Station, the largest structure ever built off-world. It took over a decade and more than 40 assembly flights to construct its 450-ton framework. A single meaningful solar power satellite would represent the equivalent of building not one, but thousands of international space stations, and they cannot all occupy the same precious slot in geostationary orbit. They would need to be carefully spaced around the entire equatorial belt, claiming vast tracts of orbital real estate. This staggering scale presents a seemingly insurmountable wall of logistics and cost. It is the primary reason the concept was shelved half a century ago. Confronting this raw physical magnitude forces a pivotal question. If we cannot possibly build it the old way, with everything fabricated on Earth and painfully launched piece by piece, then how do we build it at all? The answer lies not in bigger rockets, but in a complete reinvention of manufacturing itself, moving the factory from the bottom of the gravity well to the very place we need the product. The answer lies not in sending up a finished product, but in sending up a factory. To conquer the staggering scale of orbital construction, we must entrust the work to a new class of builders, ones perfectly suited for the void. This is the frontier of space robotics, where the dream of mega arrays hinges on fleets of autonomous assemblers, working in silent coordination in the perpetual sunlight of microgravity. Picture not astronauts in bulky suits wrestling with giant beams, but a ballet of specialized machines. Imagine robotic arms, but with a dexterity and precision far beyond today's industrial models, capable of handling gossamer thin solar films and massive structural trusses with equal grace. Their tools would not be simple welders, but multi-function heads that can print, fuse, inspect, and repair, all guided by an overarching artificial intelligence that sees the entire construction site as a single, evolving puzzle. The vision extends even further, drawing inspiration from the resilience of biological systems. Researchers are exploring concepts for machines that can not only build the satellite but also, to a limited degree, build copies of their own essential components, or at least perform complex self-repairs using onboard materials. This idea of self-replicating or self-sustaining systems is key to managing such a vast, remote project. Where would the materials for these repairs, or even for future expansion, come from? This is where the plot thickens, moving beyond Earth's supply chain. The ultimate goal is to close the loop in space itself, using three-dimensional printing systems that fabricate parts not from Earth-launched metal powder, but from raw materials harvested from the Moon or nearby asteroids. This shifts the entire economic paradigm from a constant, costly launch from Earth to establishing a permanent, in-situ resource utilization chain. Let us follow a single, hypothetical construction mission to see how this ecosystem might come together. The first wave from Earth is not the power satellite itself, but its architects, a swarm of specialized robotic assemblers and a core seed factory module. They are launched alongside standardized, smartly designed structural components, the basic beams and nodes of the future array. In orbit, the assemblers spring to life. Using advanced computer vision and real-time communication, they perform a precise, automated dance of rendezvous. A robotic arm anchored to the growing structure gently captures a new component delivered by a space tug. Another machine aligns it perfectly, while a third applies a localized bonding technique, perhaps a form of concentrated sunlight welding or sophisticated adhesive curing. Layer by layer, section by section, the skeletal framework takes shape, all without a single human hand guiding the process in real time. The success of the entire endeavor hinges on creating this resilient, autonomous industrial ecosystem far above our heads. It is a symphony of machines building power plants, all orchestrated by code and sustained by resources from the celestial bodies around them. This technological leap would represent a fundamental change in our relationship with space, transforming it from a destination we visit into a workshop where we manufacture our future. Yet, even this vision of robotic self-sufficiency runs into a stubborn, initial bottleneck. Before a single autonomous welder can spark to life, before a single gram of asteroid ore can be processed, we face the most immediate and expensive hurdle of all, getting the seed of this entire industrial revolution off the surface of Earth in the first place. For decades, the price tag of reaching orbit was the concrete wall against which the solar satellite dream repeatedly shattered. The sheer tonnage required meant that even at the optimistic launch costs of the space shuttle era, the project's budget would have rivaled the gross domestic product of entire nations. Every kilogram sent to space carried a crippling financial burden, often measured in the tens of thousands of dollars. This was the inescapable math that condemned the concept to the drawing board. But that math is now being rewritten line by line in real time. The catalyst is a quiet revolution in rocket design, moving from expendable, single-use vehicles to fully and rapidly reusable systems. Think of it not as buying a new car for every trip to the grocery store, but as refueling the family sedan. This shift in philosophy is fundamental. Companies like SpaceX have demonstrated this with their Falcon 9 rockets, landing their first stages back on Earth or on drone ships in the ocean. But the true game changer now on the horizon is a vehicle of a wholly different class, Starship. Designed from the outset for full reusability and massive payload capacity, its goal is to reduce the cost of launching mass to orbit by a factor of 100 or more. We are talking about a potential future where sending a kilogram to space costs not $20,000 but perhaps $200. This is not a minor adjustment. It is an economic earthquake that fundamentally changes what is possible. Suddenly, the calculus for a mega-array shifts. The millions of tons of initial construction materials, while still a monumental undertaking, begin to enter the realm of a large-scale global infrastructure project, akin to building a worldwide network of high-speed rail or a fleet of international airports. It transforms the endeavor from financially impossible to merely staggeringly ambitious. This dramatic cost reduction is the single most important key that has turned the solar power satellite from a perennial technology of the future back into a subject of serious engineering studies and investment. The door, once sealed shut, is now undeniably ajar, and some visionaries are already looking beyond rockets altogether, toward concepts that could make access to space as routine as taking an elevator. Ideas like the space elevator, a tethered cable stretching from the Earth's surface into geostationary orbit, or mass drivers that use electromagnetic force to launch payloads from the ground, remain in the realm of speculative materials science. Yet they highlight a crucial truth: the innovation required is not just in what we build in space, but in how we fundamentally break free from our planet's gravity well. The launch cost revolution is the essential first step, proving that the barrier is not physics, but economics and ingenuity. With that barrier falling, we can finally turn our full attention to the most critical technical puzzle of the entire system, the invisible thread that must connect the satellite to our homes, the beam of energy itself. The beam itself is the final, critical link in this chain of miracles, and it is often the point where public imagination turns to science fiction fears. The idea of a concentrated energy stream crossing the heavens can conjure images of a devastating weapon, a death ray from the sky. This powerful imagery is the single greatest misconception we must dispel, because the reality of the technology is meticulously designed to be its exact opposite, not a weapon but a lifeline. The transmission is not a single, scorching column of raw power, but a carefully engineered, diffuse flow of energy spread over a vast area with safety as its foundational principle. The engineers face a fascinating puzzle, choosing between two primary methods to send this power home, each with its own trade-offs. The first and more mature concept uses microwaves. Think of these not as the waves that heat your food, but as a specific, non-ionizing frequency, like 2.45 GHz, which is actually the same band used by many household Wi-Fi routers. This beam can pass through clouds, rain, and minor atmospheric disturbances with remarkable efficiency, making it reliable in most weather. However, to capture this diffuse, safe beam, the receiving station on Earth must be enormous, a sprawling field of simple wire mesh antennas called a Rectenna, which could span several square miles. The second contender is laser transmission. This method uses a highly focused beam of light, requiring a receiving dish only a fraction of the size of a microwave Rectenna. Its precision is extraordinary, but it faces a different challenge: the atmosphere itself. Clouds, fog, or even heavy dust can scatter and absorb the laser light, making it less reliable unless the receiving stations are built in regions with exceptionally clear skies like high deserts. So the choice becomes one of reliability versus precision, a massive ground footprint versus vulnerability to weather. But for both methods, the paramount concern is absolute safety. How do you ensure a beam carrying enough energy to power a city never wavers from its target? The answer lies in intelligent, fail-safe design. The transmitter would use what is called a phased array system, composed of thousands of small, individual emitters. By minutely adjusting the timing of each emitter, the system can not only aim the beam with incredible accuracy but also perform a crucial safety maneuver. It can defocus it in an instant. If the system's sensors detect the beam drifting even slightly from its designated ground target, the phased array can scatter the transmission, spreading the energy harmlessly into space long before it reaches the atmosphere. Furthermore, the power density at the center of the receiving station would be designed to be no more intense than the natural sunlight on a clear day, and it would quickly fade to negligible levels beyond the Rectenna's boundary. Walking into the beam's area outside the receiver would feel like stepping into a warm patch of sun, not a zone of danger. This is not a reckless experiment. It is a system engineered with layers of redundancy, where the act of missing its target is the default safe mode. The transmission enigma, therefore, is not a question of if we can do it safely, but a demonstration of how we have already designed the solutions. It transforms the beam from a symbol of fear into one of meticulous control, the final, gentle handoff in a journey that begins with raw sunlight and ends as clean electricity flowing silently into our homes. A silent beam from space must find its home on Earth. This final handoff happens not in a flashy power plant, but across a sprawling, low-tech landscape called a Rectenna. Imagine a vast field, perhaps the size of a small city, dotted with millions of simple, mesh-like antennas, each no more complex than a backyard satellite dish. They are passive collectors designed to resonate with the specific microwave frequency beamed down from orbit. As the invisible energy washes over them, these antennas perform a quiet act of conversion, transforming the microwaves back into direct current electricity. This is the ground segment, the essential anchor for our celestial power source. To minimize land use conflicts and ensure safety, these Rectenna farms would likely be situated in remote, sparsely populated areas, expansive deserts, or even constructed offshore on floating platforms. Their design is intentionally open, allowing most sunlight and rainfall to pass through. This opens a fascinating possibility for dual use. The land beneath the elevated mesh could remain productive, used for grazing livestock or cultivating certain shade-tolerant crops, transforming an energy facility into a form of vertical integration that actually mitigates its environmental footprint. But the journey of an electron is not over when it leaves the Rectenna. This newly minted electricity, now in the form of direct current, must be converted to the alternating current that powers our homes and fed into the complex, humming web of the global power grid. Here, space-based solar power reveals its most transformative potential for our terrestrial energy systems, not just as another source of watts, but as the ultimate grid stabilizer. Our current transition to renewables is hampered by their inherent variability. The wind does not always blow and the sun sets every night. This creates a challenging dance of supply and demand, often requiring backup from fossil fuel plants or massive, expensive battery arrays. A constellation of solar power satellites basking in perpetual sunlight would provide something entirely new, a constant, predictable, and dispatchable flow of baseload power. It would be the steady drumbeat in the orchestra of energy sources. Grid operators could rely on it day and night through storms and seasons, using it as a foundational pillar. This allows variable sources like wind and terrestrial solar to play their complementary roles more effectively, filling in peaks without the fear of a total drop-off. The Rectenna itself could even incorporate short-term storage, smoothing out any brief interruptions and providing instantaneous grid support. In this vision, the mega array in the sky becomes more than a power plant. It becomes the bedrock upon which a fully renewable, resilient, and global energy grid can finally be built, turning the problem of intermittency into a relic of the past. Every kilogram we launch into orbit carries a cost, and every watt of power that kilogram can produce determines the entire economic fate of the project. This relentless calculus of mass versus energy is the silent driver behind the most critical research, pushing material scientists to invent substances that defy our earthly intuitions. The goal is simple: create structures that are simultaneously feather light and fortress strong, and solar cells that capture more sunlight while weighing almost nothing. The breakthroughs here are not optional, they are the very fabric from which the mega array must be woven. Consider the skeleton of the satellite itself. Traditional aluminum or steel frameworks are far too heavy for an orbital structure measured in kilometers. The answer lies in advanced composites, materials born from the marriage of carbon fibers and specialized resins. These composites offer a strength-to-weight ratio that makes them many times lighter than steel while being just as rigid, but the innovation goes deeper. Researchers are exploring hierarchical structures, designs inspired by the efficient lattice of bird bones or the delicate yet resilient structure of a leaf's veins. These geometries provide immense strength using a minimal amount of material, creating vast, open frameworks that are mostly empty space yet can withstand the tremendous forces of launch and the constant thermal stress of orbiting between blistering sunlight and deep cold. Then there is the skin of this vast machine, the solar cells. The rigid, glass-paneled silicon cells common on Earth are far too bulky and fragile for this application. The future belongs to thin-film photovoltaics. Imagine solar cells printed onto flexible, metallic foils or polymers, thinner than a human hair and able to be rolled out like a colossal carpet in space. These films are not only lightweight but also surprisingly efficient, and their flexibility allows them to be integrated directly onto the composite framework, creating a unified, ultra-light power generating surface. But the most promising frontier might be a material that has revolutionized terrestrial solar research: perovskites. These crystalline structures can be manufactured at relatively low temperatures and tuned to absorb specific wavelengths of light with exceptional efficiency. In the vacuum of space, free from moisture and oxygen that degrade them on Earth, perovskite solar cells could achieve unprecedented performance, potentially doubling or tripling the power output for the same mass compared to current space-grade technology. Building in space means building for an environment of perpetual hazard. Micrometeoroids, tiny specks of dust traveling at hypervelocity, pose a constant threat of puncturing and degrading critical components. This is where the concept of self-healing materials enters the story. Scientists are developing polymers and composites embedded with microscopic capsules of liquid resin. When a micrometeoroid impact creates a crack, these capsules rupture, releasing the resin to flow into the damage and solidify, effectively sealing the wound autonomously. It is a form of biomimicry, giving the satellite a primitive immune system to repair minor injuries without any human intervention over its decades-long lifespan. Finally, there is the unrelenting thermal challenge. In orbit, a structure is baked on one side by unfiltered solar radiation and frozen on the shadowed side, creating stresses that can warp and break materials. To manage this, engineers rely on sophisticated reflective and emissive coatings, multi-layer insulation blankets, often with a shiny metallic exterior, act like a high-tech thermos, reflecting most of the incoming heat. Meanwhile, specialized black paints on other surfaces help radiate excess internal heat away into the void. This careful choreography of reflection and emission is what keeps the satellite's delicate electronics and power systems within their narrow operational sweet spot. These material innovations collectively achieve one transformative outcome. They drastically improve the power-to-mass ratio. It means each rocket launch delivers not just hardware, but a far greater capacity to generate electricity. This silent revolution in the laboratory is what turns the overwhelming scale of the mega array from a fantasy of tonnage into a manageable equation of efficiency. With every gram saved and every watt gained, the dream becomes more tangible, built not from the steels of the old world, but from the intelligent, resilient fabrics of the new. Geostationary orbit is a celestial parking spot of extraordinary value. It is a narrow ring, precisely 22,236 miles above the equator, where a satellite's orbital speed perfectly matches the Earth's rotation. From the ground, it seems to hang motionless in the sky, a fixed star that never sets. This unique property makes it the only practical location for our power-beaming satellites, as it allows a permanent, unwavering link between the array in space and its Rectenna on the ground. But this prized orbital belt is not an infinite resource. It is a single, circular highway in the sky, and every satellite placed there requires its own carefully assigned slot to avoid catastrophic interference, both physical and electronic. To power a significant portion of the planet, we would need to place not one or two, but thousands of these colossal structures into this exclusive zone. The spatial logistics become a puzzle of cosmic proportions. Each mega-array spanning kilometers must maintain its position with absolute precision, a process called station keeping. Even the faintest tug from solar radiation pressure or the moon's gravity must be constantly countered by tiny, precisely timed thruster bursts. Without this vigilance, a satellite would begin to drift, potentially entering the orbital lane of its neighbor. In a realm where closing speeds can be thousands of miles per hour, a collision between two such massive objects would be unthinkable, generating a cloud of high-velocity debris that could render entire sections of this precious highway unusable for centuries. This introduces the second, equally critical layer of coordination, the electromagnetic spectrum. Each power beam requires a specific radio frequency to transmit its energy, and those frequencies must be meticulously allocated to prevent one satellite's life-saving beam from interfering with another's, or with vital communication satellites sharing the same orbital neighborhood. This is not an engineering challenge one nation can solve alone. It demands unprecedented international cooperation, managed through bodies like the International Telecommunication Union, which already oversees the complex task of assigning orbital slots and frequencies for traditional satellites. The scale of a solar power satellite constellation would require a new global compact, a treaty to govern this new use of the shared orbital commons, ensuring equitable access and preventing a chaotic free-for-all in the skies. This conversation inevitably turns to the silent, growing threat already haunting all of Earth's orbits: space debris. Thousands of defunct satellites, spent rocket stages, and fragments from past collisions are already whizzing around our planet, each one a potential bullet. A mega-array with its vast, delicate solar sails would be exceptionally vulnerable to even a paint chip-sized impact. Therefore, their design must include robust debris shielding and advanced tracking systems to perform avoidance maneuvers. More importantly, their entire life cycle must be planned from the start. We cannot afford to turn these solutions into future problems. Every satellite must have a clear, funded plan for its end of life, whether that means boosting it to a distant graveyard orbit far from the operational zone, or designing it to be fully recyclable by future orbital factories. The vision of a powered world from space ultimately rests on a foundation of law and diplomacy as much as on physics and engineering. It asks humanity to demonstrate a maturity we have often struggled with on Earth, the ability to collaboratively manage a fragile, shared resource for the lasting benefit of all. Can we write the rules for the sky before we fill it with our ambitions? the sheer scale of financing required is perhaps the most intimidating barrier of all. Initial estimates suggest building a meaningful constellation of solar power satellites could cost multiple trillions of dollars, a number so vast it can feel abstract, almost fictional. But to dismiss it as impossible is to ignore the historical precedent of other civilization-scale endeavors. The Apollo program, at its peak, consumed nearly 4.5% of the entire United States federal budget. The collective investment to build the global internet infrastructure from undersea cables to data centers spanned decades and totaled in the trillions. The difference here is one of permanence and return. We are not funding a series of missions with a symbolic endpoint, but constructing a new piece of global infrastructure designed to operate for centuries. The investment would be staggering, but it would also be spread across 30, 40, or 50 years, a long-term capital project on par with constructing a worldwide network of high-speed rail or a fleet of next-generation nuclear plants. The question is not whether humanity can muster such resources, but how we choose to organize the effort. One plausible model is an international consortium, akin to the International Space Station partnership but vastly expanded, where nations pool resources, share risk, and agree on an equitable framework for distributing the resulting power. Another is a public-private partnership, where governments provide the initial anchor funding and regulatory certainty, while private companies compete to drive down construction and launch costs through innovation. A more radical vision is the creation of a new global energy utility, a neutral entity owned by its member states and tasked solely with building and operating this orbital resource for the common good. Each model carries profound geopolitical implications, demanding a level of long-term cooperation rarely seen in human history. Yet the economic argument for doing so hinges on a simple, powerful metric: the levelized cost of energy. This is the calculated average total cost to build and operate a power-generating asset over its lifetime, divided by the total energy it will produce. For a solar power satellite, the upfront capital is indeed astronomical, but once operational, the costs plummet. There is no fuel to mine, transport, or purchase. Sunlight is delivered free of charge by nature. Maintenance, while complex, would be performed by autonomous systems with minimal recurring cost. The satellite, built for a multi-century lifespan, would simply sit in the silent sunlight, converting photons into power with relentless consistency. Over a 100-year time frame, that immense initial investment gets divided by an almost unimaginable amount of generated electricity. Projections, while speculative, suggest the levelized cost could eventually fall far below any terrestrial source, including fossil fuels, nuclear, or even ground-based solar and wind when their storage and grid balancing costs are included. The payoff is not a quarterly dividend, but a permanent shift in the foundational economics of civilization, acquiring a source of ultra-cheap energy that could last for 1,000 years. This transforms the project from a costly experiment into the ultimate infrastructure investment, one that pays for itself not in profits, but in the stability and potential it unlocks for every generation to come. Control over energy has always shaped the map of global power. For over a century, that map was drawn by the geography of oil and gas, with pipelines and shipping lanes defining alliances, igniting conflicts, and concentrating immense wealth in specific regions of the world. The promise of space-based solar power presents a radical alternative, a chance to redraw that map entirely. It offers a future where the ultimate source of energy is not buried under any one nation's soil, but shines equally on all from a vantage point owned by no one. This is the profound geopolitical hope, a path toward genuine energy independence for every country that can build or access a ground station. Imagine a nation currently dependent on expensive fuel imports suddenly able to draw a steady, predictable stream of power from the sky. insulating its economy from volatile global markets and the complex politics of fossil fuel transit. It could fundamentally reshape regional dynamics, reducing a primary source of tension and conflict. The potential for a more stable, energy-secure world is immense. Yet, this hopeful vision contains a critical paradox. While the sunlight itself is free and universal, the infrastructure to capture and deliver it is not. The ability to construct, launch, and operate the mega arrays, and to control the precise technology of wireless power transmission, represents a new form of high-altitude leverage. In the early decades of such a system, this capability will likely reside with only a handful of technologically and economically advanced entities, whether they are national space agencies or colossal private corporations. This creates the risk of trading old dependencies for new ones. Instead of relying on a foreign nation for oil, a country might rely on a foreign entity for its access to the orbital power grid, for the maintenance of its Rectenna, or for the software updates that keep the beam aligned. The terms of that access, the pricing, and the conditions attached could become the new currency of international influence. We could see the emergence of space power blocks, new alliances formed not around shared borders, but around shared infrastructure in the sky. A nation hosting a critical Rectenna could gain significant diplomatic weight. A corporation that masters the robotic construction technology could hold keys to the kingdom. The equitable distribution of this resource becomes the central ethical and political question of the endeavor. Will it become a tool for inclusion, lifting nations out of energy poverty and fostering global cooperation? Or will it become another lever of control, amplifying existing inequalities on a planetary scale? The answer lies not in the technology itself, but in the frameworks we choose to build around it. This demands unprecedented international dialogue and governance, perhaps a new treaty or a global regulatory body dedicated to ensuring that space-based solar power is developed as a common benefit for humanity, with transparent rules for access, fair cost sharing, and a commitment to bridging the energy divide. The success of this project will ultimately be measured not in gigawatts alone, but in whether it brings the world closer together or casts a new shadow of division from the heavens. The promise of endless clean power from space rests on a single, vital question. Is it truly good for the Earth? To answer, we must look beyond the satellite's silent operation and examine its full story, from the roar of its launch to its final retirement. The operational benefits are profound and immediate. Once switched on, a solar power satellite generates electricity with absolutely zero carbon emissions. It requires no ongoing mining, no fracking, no pipeline scouring the landscape, and no smokestacks clouding the air. On the ground, its receiving station, the Rectenna, uses far less land than a terrestrial solar farm generating the same amount of power. A Rectenna field is largely open mesh, allowing rainfall and sunlight to reach the ground beneath it, potentially enabling dual use for agriculture. In a world straining under the environmental cost of energy extraction, this represents a breathtaking reduction in terrestrial industrial pressure. Yet the environmental ledger has another column, filled with the upfront costs of construction. The most visible impact is the carbon footprint of those thousands of necessary rocket launches. A single launch of today's rockets does release significant amounts of carbon dioxide and other compounds into the upper atmosphere. Critics rightly point out that this could negate the climate benefits for years. However, this calculation is rapidly changing. The next generation of launch vehicles, like SpaceX's Starship, is designed to burn methane. This is key because methane can be synthesized using carbon captured directly from the air, creating a closed carbon loop. When the fuel is made this way, the launches themselves could become carbon neutral. Research from institutions like the European Space Agency suggests that with such green propellants and full reusability, the carbon payback period, the time it takes for the satellite to generate enough clean power to offset the emissions from its own construction and launch, could be as short as 1 to 3 years. Compared to a lifespan measured in centuries, this is a remarkably swift return on the environmental investment. The analysis must also consider where the materials come from. Building kilometers of solar arrays and composite structures will require substantial resources. Mining and refining these materials on Earth carries its own ecological toll. This is a primary reason for the long-term vision of in-space manufacturing, using resources from the Moon or asteroids. That future would largely remove this burden from our planet's ecosystems. Until that day, sourcing materials responsibly and maximizing recycling will be critical. Finally, we must consider the local environment around the Rectenna. The low-intensity microwave beam is designed to be safe, with power densities at its center comparable to natural sunlight. Ongoing studies monitor for any subtle effects on bird migration paths, insect populations, or plant life within the receiving area. Early data suggests minimal impact, far less than the habitat loss from a coal mine or a hydroelectric dam, but conscientious, long-term monitoring will be essential. The ultimate verdict is not a simple yes or no. It is a comparison. When weighed against the relentless, planet-wide environmental cost of our current fossil fuel system, or even the land use and material demands of scaling terrestrial renewables to power the entire globe, the mega array presents a compelling case. Its environmental impact is intense but brief and localized, a one-time exertion for a permanent solution. The Earth, in this equation, is asked to bear a short, sharp sting to cure a chronic, terminal illness. The logic is inescapable, but the logistics are daunting. Constructing a civilization's worth of power stations in orbit using only materials hauled up from Earth is a recipe for exhaustion, a burden our planet's launch pads and ecosystems could scarcely bear. So the vision must evolve, turning its gaze outward to the raw materials already waiting in the void. This is the promise of in situ resource utilization, a technical term for a profoundly simple idea. We stop bringing everything from home and start building with what we find along the way. The first and most accessible quarry is our own moon. Its gray, dusty surface, called regolith, is far more valuable than it appears. It is rich in silicon, the fundamental ingredient for solar cells, and metals like aluminum and titanium, perfect for structural frames. Imagine a future lunar outpost, not just a scientific base, but the first off-world industrial park. Robotic miners would scoop up regolith, feeding it into processing plants powered by the relentless lunar sun. These facilities would use concentrated solar heat or microwaves to extract pure metals and melt the silicon-rich material, drawing it into thin, flexible wafers. In the moon's low gravity, with no atmosphere to cause oxidation or contamination, this manufacturing could achieve a purity and efficiency difficult to match on Earth. The finished components, lightweight solar films and gleaming struts, would then be launched from the lunar surface into space. Because the moon's gravity is only 1/6 of Earth's, the energy required to send a kilogram of material from there to construction orbit is a tiny fraction of the cost of launching it from our home planet. The moon becomes more than a source, it becomes a springboard, but the vision expands even further to the nomadic treasure chests of the solar system, near-Earth asteroids. These ancient rocks are time capsules containing resources that make the moon's offerings look modest. Many are classified as carbonaceous chondrites, and they are cosmic gold mines, not necessarily of gold, but of something far more precious for space industry, water. Locked within their clays and minerals are vast quantities of water ice. When harvested, this water can be split through electrolysis into hydrogen and oxygen, the fundamental components of the most efficient chemical rocket propellants. An asteroid mining operation could, in essence, become a celestial gas station. refueling construction tugs and transport vehicles right where they work, eliminating the need to haul every drop of fuel from the bottom of Earth's deep gravity well. Beyond water, these asteroids are rich in platinum group metals and iron-nickel alloys, providing all the necessary materials for building more complex machinery and electronics. The most ambitious proposals even suggest using a small asteroid's own mass, capturing it and moving it into a stable orbit near our construction zone to serve as a permanent orbiting quarry. This shifts the entire economic paradigm. Instead of a linear, Earth-centric supply chain with crippling launch costs, we create a closed-loop, in-space industrial ecosystem. The first seed factories, small and launched from Earth, would use local resources to build larger factories, which would then produce the actual power satellites. This self-replicating, expanding capability is what transforms the project from a finite, Herculean construction effort into the seed of a solar system-wide industry. The energy to power our planet could ultimately be built from the very substance of the cosmos itself, a testament not to what we take from our world, but to what we learn to make from the universe around us. A power grid spanning the heavens would be the most critical infrastructure humanity has ever created, and therefore the most tempting target. The vulnerabilities are as vast as the system itself, beginning with the satellites. Each mega-array is a complex network of computers, sensors, and thrusters, all controlled by streams of data from Earth. A malicious actor would not need to launch a physical attack to cause chaos. They could attempt to hack the command and control link, sending false instructions to a satellite. Imagine the consequences of a slight, malicious nudge from its station-keeping thrusters, slowly drifting it out of alignment until its power beam strays dangerously off target. Or consider a cyber attack that commands the vast array to fold its solar panels or, more subtly, to operate at reduced efficiency, creating an artificial and untraceable energy shortage on the ground below. The transmission beam itself presents another vector. While the beam is not a weapon when properly aimed, its integrity is everything. An adversary could attempt to jam the precise microwave or laser signal with noise, disrupting the flow of power. A more sophisticated threat is spoofing, broadcasting a counterfeit control signal to trick the satellite's transmitter into shifting its aim or altering its power output. The ground segment is equally exposed. The Rectenna farms and their connection points to the terrestrial grid are physical sites that must be secured against sabotage, while the data networks managing the flow of electricity become a digital battlefield. A successful attack would not merely cause a local blackout. It could trigger cascading failures across continents, destabilize national economies, and create geopolitical crises overnight. The security of this orbital grid is not an add-on feature, it is the bedrock upon which all other benefits rest. This demands a security paradigm leap, integrating defense into the very DNA of the system's design. The first line of defense is unbreakable communication. This is where the emerging field of quantum encryption becomes essential. Unlike traditional codes that rely on mathematical complexity, quantum key distribution uses the fundamental properties of photons to create encryption keys. Any attempt to intercept or measure these photons changes their state, immediately alerting both the sender and receiver to the eavesdropping. This would make the command channels to the satellites fundamentally tamper-proof. Next, we need incorruptible record-keeping for every command sent and every action taken. Inspired by the principles behind blockchain technology, the system could employ a distributed, consensus-based ledger for its operational logs. Every maneuver, every power adjustment would be recorded across a decentralized network of ground stations and perhaps even on the satellites themselves. No single entity could secretly alter the logs, and any unauthorized command would stand out as an anomaly rejected by the network's consensus. Finally, we need a vigilant, intelligent guardian watching over this entire ecosystem. Artificial intelligence trained on petabytes of normal operational data would constantly monitor the health and behavior of every component. It would look for the faintest signal of something wrong, a thruster firing at an odd time, a slight dip in transmission efficiency that matches a known jamming pattern, or an access request from an unauthorized location. This AI would not just detect threats, it would autonomously enact countermeasures in real time, perhaps isolating a compromised subsystem, switching to a backup communication channel, or alerting human operators to a threat they cannot yet perceive. Building this cyber fortress is not merely a technical challenge, it is a prerequisite for trust. For nations to rely on this shared power source, they must have absolute confidence in its resilience. The ultimate goal is to create a system so robust, so layered in its defenses, that the cost of attacking it outweighs any conceivable benefit, turning the orbital grid from a target into a bastion. This shifts the conversation from fear of vulnerability to the architecture of unwavering stability, where the light from the sky is not only endless but utterly dependable. The true promise of this technology lies not in the satellites themselves, but in the world they would make possible here on the ground. A world powered by nearly free, limitless clean energy is not merely an upgrade to our current system, it is a fundamental rewrite of the rules of civilization. The most immediate and profound impacts would be felt in our fight against the planet's greatest challenges. Take water scarcity. Today, turning seawater into freshwater through desalination is an energy-hungry and expensive process, limiting its use to wealthy coastal nations. With energy costs approaching zero, massive desalination plants could run continuously, transforming arid coastlines into lush, habitable regions and securing water for billions. Similarly, the daunting task of directly capturing carbon dioxide from the atmosphere, currently a costly and niche technology, could be scaled to an industrial level. We could build vast forests of machines that actively clean the air, reversing the atmospheric accumulation of greenhouse gases and giving us an active tool to manage the planet's climate. This energy abundance would ripple through every corner of the economy. The cost of manufacturing anything from building materials to electronics would tumble as the fossil fuel inputs and electricity bills that make up a significant portion of production expenses vanish. Transportation would be revolutionized not just by electric vehicles, but by the synthesis of clean electro-fuels for ships and planes, and the potential for ultra-efficient, magnetically levitated global transit networks. The digital world would expand exponentially as the energy barrier to running powerful data centers and next-generation computing like quantum machines simply disappears. For remote communities, from isolated villages to small island nations, this is the difference between energy poverty and empowerment. A single, modest Rectenna could deliver enough power to support modern healthcare, education, and industry, leveling the global playing field in a way no foreign aid program ever could. The societal shift would be deeper than economics. The monthly anxiety of an energy bill, a constant weight on household budgets and business plans, could become a relic of history. When the foundational resource for modern life is as abundant and accessible as air, it changes our relationship to work, creativity, and what we consider valuable. Human effort could shift away from jobs centered on the extraction, distribution, and management of scarce energy, and toward pursuits in exploration, art, science, and personal growth. This is the vision of a post-scarcity energy future, not a utopia without challenges, but a platform for unprecedented human potential. Yet such a radical shift does not come without its own profound questions. How do our economic systems built on scarcity adapt to a world of radical abundance? What new forms of value and purpose do we cultivate when one of the great struggles of civilization is suddenly solved? The arrival of endless power from the sky would not be an end point, but the beginning of humanity's greatest and most challenging conversation about who we are and what we choose to build next. This vision unfolds not in a sudden flash, but across a deliberate, step-by-step march through the coming decades. The journey from a laboratory concept to a planet-scale power source will be measured in phases, each building upon the lessons of the last. The first tangible steps are already on the calendar. Before this decade is out, we will likely see the first small-scale demonstrator missions take flight. Projects like those from the United States Air Force Research Laboratory or the United Kingdom's Space Energy Initiative are not designed to power cities. Their goal is far more fundamental: to prove the core technologies of efficient conversion and safe, precise wireless power transmission over orbital distances in the real environment of space. Think of these not as power plants but as critical proofs of concept, the right flyer moments for this new industry. The lessons learned from those initial demonstrations will pave the way for the next phase in the 2030s. This is when we might see the first operational, purpose-built power beaming satellite. Its initial customers will probably not be major national grids, but ideal, isolated test beds. A remote military outpost, a small island community dependent on expensive diesel generators, or a forward-operating lunar base could become the first beneficiaries. This satellite would be modest in scale but monumental in symbolism, proving that the system can reliably deliver useful, dispatchable power to a specific point on Earth or the Moon, day and night, rain or shine. It transitions the technology from an experiment to a utility. Success in that niche application sets the stage for the 2040s, the era of commercial scale. This decade could witness the launch of the first solar power satellite designed to connect directly to a terrestrial energy grid, perhaps feeding power into a national network during peak evening hours when the sun has set on ground-based solar farms. This array would be significantly larger, requiring advances in robotic assembly and likely utilizing some of the first components manufactured from lunar materials. Its operation would trigger the complex, real-world process of integrating space-based baseload power with our existing renewable infrastructure, working out the regulatory and economic models in real time. From there, the pace of deployment could accelerate through the latter half of the century. Each new array makes the next one cheaper and easier to build as the in-space industrial ecosystem matures. The construction fleets grow more capable, the supply chains become more localized to space itself, and the launch costs from Earth continue to fall. A full constellation capable of making a meaningful dent in global fossil fuel use, perhaps supplying 10 or 20% of the world's electricity, is likely a mid to late century achievement. A system robust enough to truly power the planet, serving as the bedrock of a post-scarcity energy civilization, may be the work of the entire 21st century. This phased timeline is not a delay, it is a necessity. It allows for the gradual iteration of technology, the relentless reduction of cost, and most importantly, the careful, collaborative development of the international laws and cooperative frameworks needed to steward such a powerful resource for all humanity. The countdown to a new energy dawn has already begun, one deliberate, groundbreaking decade at a time. Such a project would dwarf even the grandest national space programs of the past. We stand at a crossroads where no single nation, no matter how wealthy or technologically advanced, can or should shoulder this endeavor alone. The sheer magnitude of investment, risk, and required expertise makes a compelling case for a new kind of partnership, a modern Apollo program not for planting a flag on the moon, but for securing the future of our home planet. This would be an international consortium with a singular, unifying mission: to build the infrastructure for global energy security. We already have a blueprint for this level of cooperation floating 250 miles above us. The International Space Station stands as a testament to what is possible when geopolitical rivals choose to collaborate in orbit. For over 2 decades, it has been a shared outpost of science, built and operated by the United States, Russia, Europe, Japan, and Canada. Its success proves that even amidst tensions on Earth, a shared goal in space can create a durable framework for peaceful work. A solar power satellite consortium would need to expand this model to an unprecedented scale, incorporating not just spacefaring nations, but also those who represent the vast majority of energy consumers and future beneficiaries. The model could also draw lessons from other monumental scientific collaborations, like the ITER fusion project in France. ITER brings together 35 nations, including the United States, China, Russia, India, Japan, South Korea, and members of the European Union, all contributing components, funding, and brainpower to build a single experimental reactor. The goal is shared knowledge and a future energy source. A space-based solar power initiative would function similarly, but with a clearer, more immediate path to a tangible product: electricity flowing into the global grid. Imagine a new international entity, perhaps under the auspices of the United Nations or a newly formed Space and Energy Council, where member countries contribute according to their means. Technologically advanced nations could provide launch services, robotics, and advanced materials research. Nations with strong industrial bases could manufacture standardized components. Others could contribute financially or offer ideal locations for Rectenna sites. In return, every participating nation gains a guaranteed, equitable share of the power generated, along with the technology transfer and high-tech jobs that come from being part of the supply chain. This framework transforms the project from a potential source of geopolitical tension into a powerful tool for diplomacy. By intertwining the economic and energy futures of rival nations into a single, peaceful, and existential project, it creates a powerful incentive for stability and cooperation. The shared need for success overrides narrower conflicts. Building and protecting the orbital power grid becomes a common interest more vital than any terrestrial dispute. Such a collaborative achievement could redefine the 21st century, shifting the narrative from competition over dwindling resources to a collective triumph of human ingenuity for the common good. It offers a compelling vision where the light that powers our world also illuminates a path to a more united one. The sunlight bathing our planet costs nothing and asks for nothing in return. It is the ultimate commons, a gift from a star to a world. Yet the moment we propose building machines to harvest that light at its source, we confront a profound and ancient human question: who has the right to own what belongs to everyone? The legal and ethical framework for this endeavor is as untested as the technology itself, existing in a gray zone between earthly law and cosmic reality. The foundational document is the 1967 Outer Space Treaty, a product of the Cold War space race. Its core principles are noble and clear. Outer space is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. No nation can plant a flag on an asteroid or a plot of orbital space and call it their own. Furthermore, the treaty declares that the exploration and use of outer space shall be carried out for the benefit and in the interests of all countries, and shall be the province of all mankind. This language points toward a principle known as the common heritage of mankind, a concept later applied to the deep seabed, suggesting that certain resources belong to humanity collectively and must be managed for our shared benefit, not for private or national gain. But here the clarity ends and the complexity begins. The treaty prohibits national appropriation, but it is silent on the activities of private corporations. It encourages use for all, but does not define how the benefits of that use should be distributed. This creates a legal paradox. A company could argue that while it cannot own the space itself, it can own the satellite it builds there, and by extension, the sunlight that satellite converts into a sellable commodity. In essence, they would not be owning the sun, but owning the exclusive right to sell its power from a specific vantage point they control. This risks creating a new kind of enclosure, not of common land on Earth, but of the high frontier itself, where the most valuable orbital slots and transmission frequencies are claimed by the first and the wealthiest, locking out everyone else. The ethical stakes could not be higher. If this technology is developed under a purely commercial, first-come, first-served model, it could birth the ultimate monopoly, a cartel that controls the flow of energy to the planet. The dividends of this cosmic resource, both in staggering financial profit and in civilizational power, could become concentrated in the hands of a tiny few, amplifying global inequality to a scale we have never seen. Conversely, if governed with foresight and a commitment to the common heritage principle, it could become the greatest tool for equity in human history. Imagine a global trust independent of any single government, managing the orbital slots and licensing the technology. The revenues generated, which would be immense, could be directed not into private coffers, but into funding the United Nations Sustainable Development Goals, eradicating poverty, ensuring clean water and education worldwide, or establishing a universal basic energy allowance, a guaranteed minimum of power for every human being as a fundamental right. The choice before us is not merely technical, it is a test of our species' maturity. Will we treat the infinite light above us as just another commodity to be captured and sold, repeating the patterns of scarcity and conflict that have defined our history? Or will we see it as an opportunity to finally build a system that reflects the abundance of its source, designed from the outset to lift all of humanity together? The answer will determine whether this project becomes a beacon of unity or casts the longest shadow of all. The ultimate energy solution will not emerge from a single breakthrough, but from a portfolio of contenders, each racing to rewrite the same fundamental rules. Space-based solar power enters a crowded field of revolutionary ideas, each with its own compelling narrative and dedicated champions. To understand its true place, we must place it side by side with its most formidable rivals. First, there is the perennial dream of nuclear fusion, the process that powers the sun itself. For decades, fusion has been the energy of the future, always promising to be just 30 years away. The challenge is monumental, containing a star-like plasma at temperatures exceeding 100 million degrees Celsius within a magnetic bottle or a laser imploded pellet. Recent experiments have achieved net energy gain for fleeting instants, a historic milestone. Yet the path from a laboratory proof of concept to a reliable, economically competitive power plant remains long and extraordinarily expensive, likely measured in many more decades. Fusion's promise is immense, virtually limitless fuel from seawater and minimal long-lived radioactive waste, but its timeline and ultimate cost per kilowatt-hour are still profound unknowns. Then we have the evolution of nuclear fission, not the large light water reactors of the past, but next-generation designs. Concepts like molten salt reactors or those fueled by thorium offer significant potential improvements in safety and waste reduction. They could consume existing stockpiles of nuclear waste as fuel and are designed to be inherently meltdown-proof. Their technological readiness is higher than fusion, with several prototype projects underway. However, they still grapple with public perception challenges, the long-term issue of radioactive waste management, albeit reduced, and the capital-intensive nature of nuclear construction. Their scalability is also constrained by the availability of specialized fuel cycles and the geopolitical complexities of nuclear technology. Finally, there is the relentless here and now march of terrestrial renewables, wind and solar, supercharged by advances in gargantuan grid-scale storage. This is the incumbent favorite in the race to decarbonize. Solar panel and wind turbine efficiencies keep climbing while their costs have plummeted. the missing piece has always been storage to cover the nights and the calm periods. Solutions are scaling rapidly, from ever-cheaper lithium-ion battery farms to pumped hydro, compressed air, and flow batteries. The vision is a vast, interconnected grid where surplus power from sunny or windy regions is stored and shipped to where it is needed. The challenge is one of sheer magnitude and geography. Powering entire continents through winter nights would require storage capacities and grid interconnections on a scale that itself represents a colossal planetary engineering project, with its own significant material and land use footprints. So how does our orbital power plant stack up in this comparison? On technological readiness, it currently lags behind advanced fission and terrestrial renewables, but its core principles have been validated in small demonstrations. Its potential cost, driven by the launch revolution and in-space manufacturing, could eventually undercut all other sources due to its permanent zero fuel expense. In terms of scalability, it is arguably unmatched, limited only by our ability to build in orbit and the capacity of the geostationary belt. Its environmental footprint, after the initial carbon payback period, is arguably the lowest, requiring no fuel mining, minimal land use, and producing no operational emissions or long-term waste. This analysis reveals a crucial insight. This is not a simple horse race where only one technology can win. The future of a stable, abundant energy civilization likely lies in a diverse portfolio. Terrestrial renewables, perfectly suited for distributed generation, could power local communities and industries. Advanced nuclear fission might provide dense, reliable power for heavy industry and remote population centers. Fusion, if realized, could become another cornerstone of baseload supply, and space-based solar power, with its unique offering of constant, predictable power from a single point in the sky, could act as the ultimate grid stabilizer and baseload anchor for entire continents. In this symphony of energy sources, each plays a different, vital instrument. The orbital array does not seek to silence the others, but to provide the steady, unwavering rhythm that allows every other part of the ensemble to perform at its very best. The true test of any grand vision lies in the first, fragile steps of its realization. While the concept of beaming power from space has been validated on paper for decades, the last few years have witnessed a quiet surge of activity, moving from whiteboard diagrams to hardware actually flying in orbit. These are not the sprawling mega arrays of tomorrow, but their essential precursors, the proof of concept missions designed to answer the most fundamental questions with hard data. One of the most watched efforts comes from the California Institute of Technology. In early 2023, their space solar power project launched a pioneering payload aboard a SpaceX Falcon 9 rocket. Dubbed the Space Solar Power Demonstrator, it was not a single satellite, but a collection of 3 critical experiments bundled into one. Its most visually striking element was a deployable, flexible structure about the size of a picnic table, designed to test how ultra-lightweight solar panels could be unfurled in the zero-gravity environment. Another experiment focused on the heart of the conversion challenge, testing different types of photovoltaic cells to see which ones best withstand the harsh radiation and extreme temperature swings of space. Perhaps most crucially, the demonstrator included an array to test the wireless transmission of harvested power across a short distance within the spacecraft itself, a vital first step toward beaming energy over thousands of miles. The mission's primary goal was not to power a city, but to power confidence, proving that the core components could survive launch, deploy autonomously, and function as designed in the real space environment. On the other side of the country, researchers at the United States Naval Research Laboratory have been tackling the challenge from a different angle, focusing on the terrestrial segment of the power beaming chain. In a landmark experiment, they successfully demonstrated the wireless transmission of solar power across a military base, converting sunlight into a microwave beam and sending it over a distance of 1 kilometer to a receiving Rectenna. The amount of power delivered was modest, enough to light a few bulbs, but the significance was monumental. It proved, in a controlled, ground-based setting, the precision and safety of the entire beaming process from end to end. The beam was accurately aimed and its power density meticulously controlled, addressing public safety concerns with tangible evidence. These early missions share a common, deliberate philosophy. They are breaking down an impossibly complex megaproject into a series of solvable engineering puzzles. Each test answers a specific, narrow question. Can we manufacture solar panels thin and light enough to be economically launched in vast quantities? Can we build structures that deploy reliably without an astronaut's touch? Can we aim an energy beam with the pinpoint accuracy required for safety over continental distances? Every affirmative result, every data point gathered, is a brick in the foundation of credibility. For investors and policymakers accustomed to viewing space-based solar power as a distant fantasy, these small-scale successes are transformative. They shift the conversation from speculative physics to demonstrated engineering, providing the concrete evidence needed to secure the next round of funding for larger, more ambitious tests. The journey to the stars begins not with a leap, but with these careful, measured steps, each one proving that the path ahead is not a mirage, but a road we are already beginning to build. A new frontier demands a new kind of worker. The silent ballet of construction in orbit and the steady hum of power flowing to Earth will not be managed by magic, but by a vast, skilled workforce operating both on the ground and in the void. This endeavor will birth professions that sound like science fiction today, but will be as essential tomorrow as electricians and software developers are now. Picture the orbital construction site where the primary labor force is not human but robotic. This creates a high-skill niche for space-based robotic technicians. These will not be factory floor mechanics, but engineers and operators who specialize in remote, telepresence repair and intricate programming. From Earth, or perhaps from a nearby habitat module, they will use advanced virtual reality interfaces to see through the eyes of a malfunctioning assembler, guiding its robotic arms through a delicate repair on a solar panel array millions of miles away. Their work is a blend of extreme precision and profound patience, where a single command can take seconds to reach its target. Alongside them, a new breed of orbital traffic controllers will emerge. Their domain is not the crowded skies over an airport, but the increasingly busy lanes of geostationary orbit. They will choreograph the arrival of construction modules, the movement of robotic tugs, and the precise positioning of finished satellites, ensuring that this celestial highway remains safe and collision-free. Their screens will display a real-time map of orbiting assets, each one a multi-billion-dollar piece of critical infrastructure, and their decisions will prevent the cascading chaos of a single accident. Back on Earth, the power beam itself creates a specialized discipline. Power beam engineers will be the guardians of the transmission. They will monitor the integrity of the microwave or laser link, adjusting for atmospheric disturbances and ensuring the beam remains perfectly centered on its Rectenna target. Their work combines expertise in electromagnetics, atmospheric physics, and sophisticated software control systems. They are the stewards of safety, the ones who guarantee the invisible river of energy never wavers from its course. And before a single gram of lunar regolith is processed, we will need space resource geologists. These planetary scientists will use orbital sensors and robotic prospectors to map the composition of the Moon and near-Earth asteroids, identifying the richest deposits of silicon, metals, and water ice. Their analyses will determine where to build the first off-world quarry, turning raw celestial bodies into strategic assets. To fill these roles, our educational pipelines must evolve. The demand for science, technology, engineering, and mathematics, or STEM, expertise will be immense, but the needs go deeper. We will require specialists in space law who can navigate the complex treaties and liability issues of orbital industry. We will need masters of orbital logistics who can optimize the supply chain stretching from Earth factories to lunar processing plants to the construction zone. A new field of extraterrestrial environmental science will arise, focused not on preserving wilderness, but on understanding and mitigating the impact of our industrial activity on the space environment itself, from orbital debris to the subtle effects of power beams on the upper atmosphere. This economic ripple effect has the potential to spark a sustained orbital gold rush. Unlike historical rushes focused on extracting precious materials to bring back home, this new economy is fundamentally different. The value is not in what you take from space to Earth, but in what you build and operate in space to serve Earth. It creates a permanent, growing industrial ecosystem in orbit, one that generates not fleeting wealth, but a continuous stream of energy, innovation, and high-skill employment for generations to come. The workforce of tomorrow will look to the sky not just for inspiration, but for their livelihood, building a new chapter of human industry where the factory floor has no ceiling. The sun is not a placid, steady lamp. It is a churning sphere of plasma, capable of sudden, violent outbursts that can lash out across the solar system. For a civilization planning to build its primary power grid in that very environment, this is not a minor concern, but an existential engineering challenge. The mega-arrays would be positioned directly in the line of fire, exposed to the full spectrum of what we call space weather. The most dramatic events are coronal mass ejections, billion-ton clouds of magnetized solar plasma hurled into space at millions of miles per hour, and solar flares, intense bursts of radiation. When these storms wash over a satellite, they do not just create a pretty aurora. They induce massive, destructive electrical currents in any long conductor, like the kilometers of wiring and metal framework in our power arrays. The surge could silently fry sensitive electronics, degrade solar cells, and cripple the satellite's ability to function, turning a multi-billion-dollar asset into silent, orbiting scrap. For a system intended as the bedrock of global energy, such a vulnerability is unacceptable. The solution is not to avoid the storms, which is impossible, but to engineer a resilience that can weather them. This begins with a fundamental redesign of the satellite's nervous system. Electronics would need to be hardened, shielded within layers of specialized materials, perhaps even housed in compartments lined with water or polyethylene, substances excellent at absorbing harmful radiation. Think of it as building a fortress for microchips, where the walls themselves are designed to soak up the incoming barrage. But shielding has its limits against the most powerful events. For these, engineers propose a more dynamic defense, the creation of internal storm shelters. During a warning period, the most delicate components, like central processors and communication hubs, could be physically moved or electronically isolated into these heavily shielded cores, while the rest of the array weathers the storm. The vast solar panels and structural beams, being simpler and more robust, could be designed to simply endure the temporary surge, much like a tall tree bends in a hurricane. The true key to this strategy, however, lies not in orbit but back on Earth in our ability to predict. Space weather forecasting is advancing rapidly. Satellites like NAS, a deep space climate observatory, act as solar sentinels, positioned between the Earth and the Sun, giving us crucial advance warning, sometimes up to a day, of an incoming coronal mass ejection. With that precious lead time, operators could execute a carefully planned sequence. They could command the satellite to temporarily power down non-essential systems, angle its solar panels to minimize exposure, and reconfigure its electrical pathways to shunt induced currents safely away from critical components. It is a cosmic dance of preparation where the satellite tucks in its vulnerable parts before the storm hits. This transforms the satellite from a passive target into an active participant in its own survival. Reliability in the face of such raw celestial power is not an added feature, it is the very proof of concept. A grid that can shrug off the fury of the sun itself is a grid worthy of powering our world. From our planet's surface, the mega-arrays would not dominate the night sky. At their staggering altitude of 22,000 miles, each colossal structure would shrink to a mere pinprick of light. To the unaided eye, they would likely appear as a new set of faint, unmoving stars, perhaps forming a delicate, artificial belt strung loosely along the celestial equator. They would not outshine Venus or cast shadows on the ground. Their visual presence would be subtle, but for astronomers and stargazers, even this faint glow presents a challenge. To mitigate this, engineers are already considering smart design choices. The arrays could be constructed from ultra-dark, non-reflective composites, and their vast solar panels could be angled to scatter sunlight away from Earth rather than reflecting it directly back at us, much like tilting a mirror away from a window. The goal is to make these technological leviathans as visually silent as possible, preserving the natural beauty of the cosmos for scientific observation and human wonder. Yet their very existence would be a profound new fact in the human experience. For the first time in history, a permanent, human-made constellation would hang in the heavens, visible from every continent. These silent, shining sentinels would be more than just machinery. They would become a constant, visible reminder of our own ingenuity, a testament to what our species can achieve when we aim beyond terrestrial limits. Every clear night, anyone looking up could see a gentle proof of our interconnectedness, a shared technology operating far above the atmosphere that powers lives below. This could forge a powerful, unifying symbol for the planet. Unlike national flags or borders, this celestial infrastructure would belong to no one and everyone simultaneously, a quiet beacon of collective effort. It might inspire a renewed sense of global citizenship, a tangible link in the sky reminding us that we are all, quite literally, powered by the same star and the same extraordinary endeavor. The night sky has always told stories of gods and heroes. Now it might begin to tell a new story, one of shared responsibility and breathtaking collaboration written in faint, patient light. Building a power grid for Earth is not the final destination, but the essential training ground for a far greater journey. The technologies and industries forged to create these orbital arrays will become the foundational toolkit for humanity's next chapter, transforming us from a planet-bound species into a truly spacefaring civilization. Consider the immediate next steps. The very same robotic assemblers and in situ resource utilization plants designed to build solar satellites around Earth are precisely what we need to establish permanent, self-sustaining outposts on the Moon and Mars. Instead of beaming power 36,000 kilometers down to Earth, we could beam it a few hundred kilometers across the lunar surface, providing relentless energy to a sprawling research base, a mining operation, or a greenhouse colony, all without the crippling limitations of a 2-week lunar night. The economic model is circular and self-reinforcing. The revenue generated from selling clean power to Earth creates a massive, stable funding stream, a financial engine that can be reinvested into pushing deeper into the solar system. It transforms space from a cost center funded by government budgets and symbolic flags into a profitable industrial domain with its own growth logic. This shift is profound. It means the expansion into space is no longer a discretionary expense, but a natural extension of a thriving new economic sector. With that foundation, our ambitions can scale to concepts that today seem purely visionary. Take the idea of interstellar travel. One of the greatest challenges for sending probes to nearby stars is providing them with enough power to communicate back to us across the light years. A future iteration of our power beaming technology could solve this. Envision a network of gigantic solar arrays positioned in the outer solar system, perhaps near Jupiter, where sunlight is weaker but the infrastructure exists to harness it. These stations could fire concentrated laser beams at interstellar probes, providing them with power for propulsion and communication long after their onboard nuclear batteries fade, acting as celestial lighthouses guiding our first messages to the stars. Further out on the horizon of possibility lie the true megastructures like O'Neill cylinders, vast rotating space habitats designed to house millions in Earth-like conditions. The energy and material requirements for such an undertaking are almost beyond comprehension, yet they are built from the same core competencies: massive orbital construction, resource harvesting from asteroids, and the management of colossal, closed-loop life support systems. A civilization that has mastered building power arrays measuring kilometers across has already developed the industrial muscle and logistical genius needed to contemplate stitching together continents worth of living space in the void. In this grandest view, the satellites powering our planet become more than utility projects. They are the first apprenticeships in a new kind of architecture. They teach us how to work with the fabric of space itself, using the raw materials of the cosmos to build the infrastructure for our own future. The light we capture today to illuminate our cities could, centuries from now, be the same light that nurtures gardens on distant moons, propels our first emissaries to other suns, and finally fulfills the oldest human dream of finding our place among the stars. The blueprint for a new energy age now lies before us, not as fantasy, but as a series of solvable equations. We have traced its arc from a spark in a writer's mind, through decades of patient study, to the first small demonstrators quietly beaming power in the vacuum of space. The scale remains almost incomprehensible, a construction project spanning generations and demanding cooperation on a level we have never before achieved. We have stared directly at the barriers of cost, the perils of orbital debris, the sheer audacity of building cities in the sky, and found not dead ends but frontiers of innovation. The answers are taking shape in autonomous robotic swarms, in materials born from atomic-scale design, and in the quiet revolution of rockets that land themselves to fly again. This endeavor asks everything of our ingenuity, and in return, it promises nothing less than a fundamental rewrite of the human condition. A world powered by the silent, constant light from above is a world freed from the ancient struggles over scarce resources. It redefines security, stability, and possibility for every nation and every community. The journey will be long, measured in decades, not years. There will be setbacks, debates, and moments where the challenge seems too great. But the direction is clear. We are no longer wondering if such a thing is possible within the laws of physics. We are now grappling with the more human questions of will, of wisdom, and of shared purpose. How we choose to answer those questions will determine the legacy of our century. Will we build a new commons in the sky for the benefit of all, or will we repeat the old patterns of enclosure and control? The stars have always been a mirror for our ambitions. Soon, they may become the source of our power, a permanent testament to what we can achieve when we look upward and decide to build a better future together. If this vision of a connected, abundant world resonates with you, consider subscribing. We will be here tracking each step of this monumental journey as it